Hello friends. So in this video let us try to understand about shear stresses. First the sign convention, and then later on we will see how shear stresses are complementary to each other. So let us take to understand the better picture under the action of shear stresses. Let us try to take the element, small element, which can be of any material, which is a rectangular parallelepiped which is having the sides ABC. And which is also, suppose it is having the sides of one of the sides are A, then the other side is B, and third side as C. This ABC of course coinciding with the axis, which is A, X, Y and Z. So suppose that shear stress tau, which is being acting on the top surface. Of course the back side and the front side, the rear side and front side are free from shear stresses, and on the top let us say I am having the shear stress which is acting on uniformly in the tangential direction of the stress element. Okay, this is the rectangular parallelepiped having sides ABC, where ABC is coinciding with the XYZ axis, and front and rear elements are sides are free from shear stresses. Now this tau is distributed uniformly. Of course this is the stress. So how do you define the positive set of shear stresses? Of course under the action of this shear stress, the shear stress, first we will define the planes, positive planes and negative planes. Let us say positive planes are defined, let us say XYZ, the plane is defined by its normal, so XYZ axis, the planes which are perpendicular to the XYZ axis. For example, for X axis the perpendicular face is this, so this is X plane, but the plane which is going on the positive direction, which is there on the positive side, right hand side, is called as positive X plane. So this is a positive plane. Similarly the plane perpendicular to the Z axis, this is positive Z plane, and which is towards the positive Z axis, this is the positive Y plane, because it is towards the positive y axis and perpendicular. So plane is defined by its normal, the perpendicular plane, that is positive x, y and z plane we have defined, and the opposites are defined as negative planes. So this is your negative x plane, this is your negative y plane, and this is your negative z plane. Okay, so how do you define the positive set of shear stresses? If the shear stresses are acting on positive planes and in positive direction, those stresses are positive shear stresses, and at the same time if shear stresses are acting on negative planes in negative direction, are also positive shear stresses. So shear stress is acting on positive. For example, here you can see this is a positive y plane and shear stress is acting in positive x axis. Suppose shear stress acting in on negative y plane, but in negative x axis. So this is the example. If top, you can see here tau, where shear stress is acting on positive direction, positive x axis. This shear stress acting on negative direction, which is acting on in negative plane and negative y direction, is also called as positive shear stress. So positive planes and positive direction. Now what will be the resultant effect of this cube, the shear stresses? Of course, if I imagine the cube which is having the, of course there has to be equal and opposite shear force. If this is shear stress acting in positive x direction, y direction and z direction, then there has to be equal and opposite force on the bottom negative y plane as well. So equal and opposite force, the pair of shear stresses has to be there. Now the effect of this and shear stress which is acting on the positive plane, that is positive x plane and positive y direction, this is on the right hand side, this shear stress is acting, and similarly the equal and opposite shear stress which is acting on the negative x plane and negative y direction is also positive shear. So this four set of shear stress, the entire set is positive shear stresses. Now another effect you can see that this effect under the action of these shear stresses, there will be a change in the angle, of course, due to this shear stress. So your shape of your shear stress cube will become something like rhomboid. Okay, the distorted shape, and you will be able to see if you draw the the straight lines of the sides of the cube, you will be able to notice that here the earlier this was 90 degree of the sides between two sides of the shear stresses, that is if this is 90 degree and if it becomes the less than 90 degree, that is this is basically this angle becomes, if this is gamma by 2 and this is gamma by 2, I can say this is 90 minus gamma, or sorry, it is pi by 2 minus gamma, and you will, under the action of this shear stresses, you will be able to see this distortion. Similarly, the opposite angle is also the pi by 2 minus gamma. However, the where is increase, you can see here the opposite angles are increasing pi by 2 plus gamma and pi by 2. So this set of shear stresses are called as, if your sides of the shear stress, let us say ABC, sides between AB, angle between AB and BC reduces, or ABCD, the angle between DC and DA reduces by the angle becomes pi by 2 minus gamma, pi by 2 minus gamma, then shear stresses are positive. And if opposite angles, that is the sides between angle between AD and AB, and also the angle between BC and CD, if it increases by pi by 2 plus if it becomes pi by 2 plus gamma, then you can say that also shear stresses are positive shear stresses. So, the complete set of shear stresses are called as positive, whereas what is negative shear stresses? The shear stresses which is acting on the negative plane and positive direction, or shear stress is acting on positive plane and in negative direction, then it is called as negative set of shear stresses. So, in that case, of course, the angle between the sides will increase, this angle between AB and BC will increase, and the vice versa situation. So, you have to imagine how the positive set of shear stresses, let us say if this is my positive x plane, but shear stress is acting in negative direction, that is downward direction, and the equal and opposite shear stress. So, these are the negative set of shear stresses. And the change in the angle, I told you the vice versa situation will become the for the negative shear stresses. So, positive plane, negative direction, and if shear stress is acting in on negative planes and positive direction are negative shear stresses. So, complete set of stress, complete set of shear stresses, whether it is not that one shear stress independently will become negative or positive, that entire set of stress will become positive or negative, and so. Okay, now we will try to see how you can prove that all the shear stresses which is acting here on top and bottom and right and left side are same. So, let us define if this is your tau 1 and this is your tau 2. Now, supposing this shear stress and this shear stress which are acting in parallel planes and equal and opposite with each other. So, they will form a kind of couple, right. The forces acting in opposite direction and on parallel planes, and if the perpendicular distance between these two is d, then these two forces will create a couple. Similarly, here tau 1 here in the front right hand side and the left hand side, and tau 2 here the top and the bottom. Both the shear stresses will create a couple. So, right hand side and left hand side, and of course, we are going to multiply it with the, to get the force we are going to multiply it with the dimensions. Okay, so I know that this is your A, this is your C and this is your B. So, tau 1 BC, okay, tau 1 times B into C will give you a force tau 1 multiply by B into C. I will redraw that figure again. This is your tau 2, this is your tau 1. So, this is a force, and equal and opposite, I told you the force is equal and opposite, and the perpendicular distance between that, this is A, this is B and this is C. So, times A, this will create a couple, and which is acting in the counterclockwise direction. Okay, this is going to create a couple, counterclockwise couple, moment, right. And similarly, this tau 2 is going to produce, which is equal and opposite in direction, and what is the force? So tau 2 multiplied by C and A is a force multiplied by perpendicular distance, that is B, is going to give you the clockwise moment, clockwise moment. Now, from the requirement, as you know, that not only the force requirement, but also in any solid body we also have the moment equilibrium requirement. So, this counterclockwise and clockwise movement both has to be, summation of this moment has to be 0. So, if I write the equation like moment equilibrium equation, then I can write sigma m about, it will create the moment about z axis. Of course, you can see here, this is your x, this is your y, and this is your z, and both the moments will create the moment about z axis, the right hand thumb rule. So, this is going to be 0. So, one is of course the clockwise and second one is counterclockwise. So, tau 1 B C A, if I consider counterclockwise positive, minus tau 2 C A B is equal to 0. And we can prove here that ABC are constant. We can get rid of this, we can easily prove that tau 1 is equal to. So, we have proved that shear stresses are complementary and shear stresses acting on the opposite faces of the element are equal and opposite in direction. Okay. And basically you can see here, if the perpendicular shear stresses on perpendicular faces of an element are equal in magnitude and have directions where both the stresses point towards or point away. You can see here the stresses point towards, and this stresses point away on the perpendicular faces. So, we have proved that shear stresses are complementary to each other, and all faces, the shear stresses, the magnitude of the shear stresses are equal, and that is we can say the complementary shear stress formula is achieved. So, we further investigate about how the shear stresses will behave on inclined section as well. So, in our next part we will try to see how the shear stresses are calculated on, basically knowing this shear stress or knowing the case of pure shear. This is a case of pure shear. There are cases, there are examples. What are the practical examples where the shear stresses are occurring? One is of course in case of beam bending, we have the shear stresses. Pure shear stress is a case where you have the torsion. We will try to investigate the torsion also, and the application of this pure shear stress element over there. And knowing this shear stresses, we also have to investigate how this is going to help us, this set of shear stress is going to help us in evaluating the stress on the inclined section as well. Okay, thank you.